with uncertain wind generation via interval optimization. It will be presented by Mr. Yao Wen Wu. Yao Wen Wu received his bachelor's degree in automation from Huanzhong University of Science and Technology, Wuhan, China in 2011, and the master's degree in electrical engineering from the University of Connecticut, Storrs in 2014. He is currently pursuing his PhD degree at the University of Connecticut. His research interests include power system optimization, grid integration, and renewable energy and economics of electricity markets. Yao Wen. The floor is yours.
Okay. Thank you, Chair, for introduction. Good afternoon, everyone. This is a joint work between UConn and ISO New England. This paper develops a novel interval optimization approach for security constraint unit commitment with M-1 transmission continuances and wind generation. The motivation is to keep the lights on the different types of uncertainty. The first type is contingencies. So transmission contingency is a sudden outage of a transmission line. So it's a discrete event. Wind generation in megawatt is continuous because both contingencies and wind generation can happen together and cause system violations. Joint consideration is critical. Then what are the difficulties? First, for contingencies, there are a large number of them. For example, in a system with 1,000 transmission lines, then there will be 1,000 corresponding transmission contingencies. And the existing approaches consider them one at a time, so which is complicated. For wind generation, I think it's known to everybody in this session that it's kind of intermittent renewable resource. So one common method to model this is stochastic programming, basically sample and reduce scenarios. If we consider them together, then there is a combined difficulty. And probably because of the above difficulties, we found few publications on the joint consideration. And then what kind of results we want to obtain? First, for contingencies, we want to capture multiple contingencies in one case to much reduce the complexity. Second, we want to model wind in a consistent framework as contingencies so that the UC solutions will be guaranteed to be feasible against all contingencies and wind realizations. Then how to do that? First, we look at the contingencies. The transmission capacity constraints means that the power flow along a line is within the transmission capacity. We write down this DC power flow equation that a power flow is a weighted sum of nodal injections weighted by those generation shift factors within this capacity. Because the GSF is the sensitivity of power flow with respect to nodal injections under contingency C. So at contingency 1, we have one of these constraints. For contingency 2, we get another. Then if we have n contingencies, we get n of these constraints. And as I mentioned, n can be a large number, so this is complicated. The observation is that all these contingencies are essentially captured by multiple possible GSF values, and they are input parameters. Then to reduce this complexity, our novel idea is to treat GSF as uncertain parameters varying within those intervals. Then we convert those multiple possible of GSF, we cover them in an interval of GSF, as in this equation. And we convert discrete events into continuous. And then interval inequality can be applied to convert this equation into one linear constraint. Then the major advantage of this model is that it can capture multiple contingencies in one constraint. So the problem size is much reduced, while we can still guarantee that M-1 contingencies are feasible. Then there is a trade-off between complexity and conservativeness. The new model can be conservative because interval optimization somehow ignores the dependency of GSF on contingency. This is for contingencies. Then how to handle wind? Wind generation as another level. of difficulty to this problem. As I mentioned, wind generation is continuous, so it can be directly modeled by intervals in a consistent framework. The issue here is that if we directly consider the worst case wind realization and the worst case contingencies together, the result can be over-conservative. To reduce this conservativeness, our idea here is to fix one type of uncertainty to its normal case or expected value and consider the extreme cases of the other one. Then we have those two combinations and we consider them in the model. The overall model is linear and can be solved by branch and cut. We have tested this modified IEEE reliability test system with 6 additional wind farms. The wind penetration level is 18.9. For comparison purposes, we use the deterministic approach as a control group and compare results with the interval approach. Then for transmission contingencies, basically it's managed by M-1 security constraint OPF. Wind generation is modeled as expected realization plus spinning reserve. After we solve the model with those two approaches, we want to evaluate the results based on simulation. In simulation, we still use M-1 security constraint OPF, but for wind generation, we sample 1,000 wind scenarios. The optimization and the simulation results are summarized in this table. Here, I want to emphasize 2 points. First, for those out of 1,000 scenarios, we found there is 0 violation in the new method, which means the solution is robust against contingencies and wind realizations. Second, the simulation cost of the new approach is 2.55% lower than that of the deterministic approach, which is significant. In conclusion, in this paper, we developed a novel SCAC problem formulation with the main contributions that it captures multiple contingencies in one constraint through a novel interval model. And also, we model wind generation by intervals so that it can be managed in a consistent framework. There are also some further developments done by us. First, we alleviate the conservativeness of the model by reducing the ranges of GSS. Second, we improve the computational efficiency based on a combination of surrogate Lagrangian regularization and branch and cut. Surrogate Lagrangian regularization is one advanced decomposition and coordination method developed in our lab. We have also tested the IEEE 180-month system for this model and approach. The broader impact of this paper is that this opens a novel and effective way to capture multiple individual cases by one group. Thank you very much for your attention. If you have any question, you're welcome to discuss with me in the post session. The post number is 1045.